Hello students, in this session we are going to study torque and power transmitted by the shaft. Right. So suppose we have a shaft, we have this shaft, it has certain dia, D dia, and it is circular in nature, solid shaft. This is a solid shaft, a torque is applied, and we want to find out this torque in terms of shear stress, right? And it has some diameter, say D is the dia of this solid shaft. We want to find out the torque in terms of shear stress, right? And vice versa, because that ready-made formula can be used wherever required in numericals, right? So what is torque? What is torsional equation? Remind the torsional equation: T by J equal to tau by R equal to G theta upon L. You should remember this: T by J, tau by R, G theta upon L, right? And suppose shear stress is given to us and we want to find out torque, or vice versa, right? So torque T will be equal to J by R multiplied by tau. J is polar moment of inertia, R is the radius at which the shear stress is obtained, and tau is the shear stress at a radius R. And you know that polar moment of inertia will be given by pi by 32 d to the power 4 for a solid shaft. This you should remember, we have shown this in the previous lecture. Put here, you will get T will be equal to J, T is pi by 32 d to the power 4, and what is R? R is d by 2 multiplied by tau. So this is the torque in terms of shear stress for a solid shaft. So this is a solid shaft, right? So solve it and you will get the torque will be equal to pi by 16 d cube multiplied by tau. So this is the torque of a solid shaft in terms of shear stress. You should remember this formula directly, right? And what else? If the shear stress is given and we want to find out the torque, then you can find out from this formula only. If shear stress is given, we want to find out torque, use this formula. If torque is given and you want to find out shear stress, then again we can make a ready-made formula for that. That tau will be equal to 16t by pi d cube. This formula should be remembered. So these two formulas should be remembered for a solid circular shaft. So this is for solid shaft, right? So this is the torque formula and shear stress formula for a solid shaft. Now we want to find out the same formula for a hollow shaft. So hollow shaft. Now suppose we have hollow shaft. And for hollow shaft, suppose this is our hollow shaft, suppose. This is the hollow shaft and material is here only, and inner dia is given small d, outer dia is capital D. Inner dia, outer dia, and we want to find out hollow shaft. You should know this equation is valid here also. You should know the polar moment of inertia for a hollow shaft, that will be equal to pi by 32 outer dia to the 4 minus inner dia to the power 4, right? You should remember this. We have already used this equation in the previous lecture, right? So put here T by J, tau by R. So T will be equal to J by R multiplied by tau. So T will be equal to, put here the values, pi by 32 d to the power 4 minus d to the power 4 divided by this radius R. R, what is R? Small r. This is the outer radius, right? Basically this is the radius at certain point. So if we are looking for the maximum torque, then we should use the outer radius. Here also we have used the outer radius D. It means outer radius D means that we are using the maximum shear stress here, tau max, right? Tau max will, the torque will related to tau max, or tau max related to the maximum torque, right? Right. So here also if we are using the outer dia, outer radius, so it means we are using the maximum shear stress, right? So this will be d by 2 outer radius multiplied by, now it will become the tau max, maximum shear stress. Is it okay? So this will be maximum shear stress. Here also you should use the term tau max, right? And here also tau max for maximum torque. So T will be equal to, what will be the T? Torque, maximum torque. That will be equal to maximum torque taken by the shaft. That will be equal to pi by 16 d to the power 4 minus d to the power 4 divided by capital D multiplied by tau max. This is the maximum torque transmitted by the shaft. Maximum torque transmitted by the shaft, right? And if you want to find out in a reverse nature what is tau max, that will be equal to 16 T d by pi d to the power 4 minus d to the power 4. So this is the maximum shear stress transmitted by hollow shaft. Maximum shear stress transmitted by hollow shaft, right? And tau max will be at the outer radius, right? So if you want to draw the shear stress diagram for this, so how you will make the shear stress diagram for a hollow shaft? Shear stress diagram for a hollow shaft, how you will make? This is hollow from inside, so there is no stress in this part. This is hollow, so there is no stress because this is a free space, right? And in the outer part there will be stress developed, and it is increasing to the outer periphery, right? Like this. So this will be the stress, right? And again in this part there will be some stress, and it will be increasing to the maximum like this. So this will be the stress developed in this hollow shaft, right? This is the way of showing the stress in hollow shaft, right? So this is a hollow part, and then there is stress, and this part, this variation and this variation will matches to each other and passing through the center. So if you extend it, although there is no stress, but if you extend it, you will get this type of curve, right? In between there is no stress, and because this is a hollow part, there is no material is there, and this is the stress starting from the inner dia to the outer dia, and this is tau max. This is tau max at outer dia, at the outer dia of this, like this. At outer dia, shear stress is maximum. Maximum shear stress is there at the outer dia. So this is the way of showing the shear stress in a hollow shaft. And in solid shaft, we have already discussed the stress, how to show the stress. This is very easy in showing this. So this is our solid shaft, and you can show here like this and this, like this, right? So this is the way of showing the shear stress in a solid shaft, right? And there will be maximum stress at the outer periphery. Tau max will be the outer periphery, right? So here this is the maximum torque transmitted by the shaft, where we are using tau max. If it is given that maximum shear stress is this much torque is transferred by the solid shaft, which is pi by 16 d cube tau max. And if torque is given, then maximum stress can be obtained from this equation using the outer periphery dia of the shaft, right? And in hollow shaft, the same thing is there. This is the torque transmitted. So suppose this is equation number 3, and this is the maximum shear stress in terms of torque and dia, outer dia. Capital D dia should be used, the outer dia of the hollow shaft. in the equations, in the calculations. So this is the equation for hollow shaft. You should remember this, right? And what is the power transmitted? Power transmitted by the shaft. Power transmitted by the shaft. What is power? Power is torque multiplied by omega. You know that in linear power transmission, the power is given by force multiplied by velocity. Force multiplied by velocity. You should remember this. So in rotation, this force is replaced by torque, and this linear velocity is replaced by angular velocity. So power is equal to T omega or omega T, right? Omega T or T omega. So this will be equal to 2 pi n T upon 60, because angular velocity is given by 2 pi n upon 60 if n is given in RPM, revolution per minute. If n is given in revolutions per minute, then the omega is given by 2 pi n upon 60. You know from basic circular motion, you have read a lot about this. So power will be given by 2 pi nt upon 60, this much kilowatt. This much kilowatt of power is transmitted by the shaft, and torque, this is the maximum power transmitted by the shaft, and torque will be taken from this equation number 1 for solid shaft, and equation number 3 for hollow shaft. Use this torque in this equation of power, and you will get the maximum power transmitted by the shaft and maximum torque which will be transmitted by the shaft.